we spent a good deal of time trying to figure out how to find the electric field due to a distribution of charges. And the reason for doing that is once we have the electric field, then if we drop a charge in, we know the force on that charge. This is the charge that got dropped in. That tells you the charge times the electric field tells us about the force. Well, this force is conservative. It doesn't matter how you get from one place, point 1 to point 2, what path you take. The force only depends on your positions, right? It depends on how far away you are from the other charges. So this is a conservative force, which means that if we think back to our Physics 1, when we did Physics 1, we started with kinematics, and then we went to forces, and then the next thing was to say for conservative forces, let's not only calculate the work, but then find the potential associated with that. So that's what we're going to do. So we're going to say, suppose we have two charges. So we're going to have our two charges. One of them is going to be glued, and we can sort of think about the energy, okay, the potential energy. So if we start with one charge, let's say it's plus Q, and it's at the origin, and it's fixed in place, it's glued. And so there's another charge, we'll call it, it's positive, let's say it's capital Q, and it starts at this point A, and when it's released, it's obviously going to move away. And so if this one's glued down, otherwise they both go from each other, but it's going to move away, and let's ask how fast it's going at point B, right? Now we could calculate this force, but the force changes because the electric field changes with distance. So it's not a constant acceleration. So we can't, we can set up F equals ma, but the acceleration isn't constant. So then we can't easily calculate it. You don't have the mathematics for that at this point. And so instead, let's look first to find the potential energy. Let's look first at the work that's done, and then we can use work kinetic energy, and then we can generalize to potential energy. So if you remember from Physics 1, the work is equal to F dot dr, where the force is changing. This is a little bit of work that's done, and what we needed to do was to add up all those pieces. And in Physics 1, you probably didn't do this integral because some people were still taking calculus at the time. But now you've all had calculus, so we can say the work is equal to the force times whatever displacement. This is a dot product, but if we look at this, in this case, I've got force going this direction, and then the direction of dr is also along the same line. It's not like this is moving across the electric field lines or across the direction of the force. So the angle between those is 0, so I can just say it's the magnitude of the force times the magnitude of dr. I can write this as from integral from A to B. The force is just K, Coulomb's law, little q, big Q, over r squared dr. And so we do this integral. Now, the K, the little q, and the big Q are all constants, so we can pull those out. So the work becomes K Q times big Q. This integral is r to the minus 2 dr from A to B. So we use our power rule. So with integrals, remember that if we've got the integral of something to some power, it becomes, I'll put it over here. Integral x to the nth dx just becomes x to the n plus 1 over n plus 1. Hopefully that looks familiar. And so this over here becomes K, Q times big Q. This is r to the minus 2 plus 1, so r to the minus 1 over minus 1, evaluated from A to B. And so this gives me minus K, little q, big Q. R to the minus 1 is 1 over r, so 1 over B minus 1 over A. And that is the work done on this charge. And so we can equate that work done with the kinetic energy using the work kinetic energy theorem. But we can recognize that will tell us if this happens to be 10 centimeters and this happens to be 4, we can find that work done. And then if this started from rest, that'll give us the kinetic energy. So work kinetic energy just says the work done is equal to the change in kinetic energy there. Okay, so because the work total is equal to the change in kinetic energy, the other thing we can do is we can say the work, you probably don't remember this from Physics 1, but we developed this potential energy as the minus the work done. And usually we have to pick a reference point. So for gravitational potential energy, we picked the reference point usually of y equals 0, often the lowest point in our setup. For a spring, we picked the potential energy of 0 to be when the spring was at equilibrium. For this kind of situation, generally what we're interested in is our reference point, because it's always about a change of potential energy, but our reference point, so in reference to a point really far away, we say our reference is that u is equal to 0 at a point really far away, at r goes to infinity. And so when we want to talk about the potential energy, we would describe this as having more and more potential energy the closer it is to plus q. So what we would do is we'll set this up again. So we'll say here's our plus little q, and here's our capital Q. And if we want to know the potential energy right at this point, at some distance r0 away, what we tend to do is say that, well, if it started way off screen at r equals infinity and came into that would tell us our potential energy. So we would say our potential energy, or a change in potential, where 0 is way out there, is equal to minus the work. So we've got this same integral, minus k q q over r squared. And now we're going to say we're going from infinity to r0. Okay? And so this u, and well, we'll call it change in u, and then I'll pick that. This will just give us the same thing. Okay, we got a minus sign, but anyway, k q q times, this is now r to the minus 1 over minus 1. Those are our limits of integration. Of course, we put this one in first, and so this gives us, these minus signs cancel, and so this delta u is equal to k q q over r0 minus k q q over basically infinity, which is 0, right? So that's going off to 0 as this r, this infinity, 1 over infinity, or as we go out to infinity, that makes this term go to 0. So this is our reference point. So in general, when we want to talk about the potential energy of a system like this, we compare it to the potential energy when this is really far away, because there we don't think of it having any potential energy. So we would say at this point, it has a certain amount of potential energy, k q times big Q over r naught. If we come in even closer, that's going to be more potential energy. So this sets us up for our description of potential energy, where this is now what we would call our potential energy, where we would say our reference point is equal to 0 as r goes to infinity. And so that's typically how we write our potential energy. Okay, so we have, using force equals QE, we found that our potential energy for a point charge, for a system where we had 2 point charges, was equal to K little q big Q over R. So our system was, we had here Q, and we had Q, big Q, and this is R, where we said the reference point was R going to infinity is where U is equal to 0. Okay, so that's connected to our force. But we spent a lot of time talking about electric field because we had said electric field is sort of what we imagine when we take the force. We say, what would be the force if we had removed this small q? And so there is something equivalent to this where we divide by q, and we call it the electric potential. So this is electric potential energy, electric potential energy, and then this, which is U, it's really delta V equals delta U over Q. And so that is equal to, this is a change in potential, is what it's called, electrostatic potential. It's not energy. And it has units, this delta V has units of joules over coulomb, which we call a volt. So when we have, say, a 12-volt battery, like this, car battery. So what that means is that one terminal, the positive terminal, is 12 volts higher than this. Think of it as like higher and then goes lower. And what that means is if I put a plus charge here, right, it will have 12 times the charge joules of energy. So if I take this, the potential energy the charge will have, the potential energy available will equal whatever the charge is times this 12 volts. And if it starts with 12 volts and then it goes along something, we don't want a straight wire here for reasons we'll talk about later, but if it did, then it would pick up, it would exchange this amount of potential energy for kinetic energy. So we can set up a situation. The most common way of doing this is not really with a battery, but if I set up sort of a situation here where I have 12 volts, this is at 12 volts and this is 0, this is our reference point now, often called ground, then we could set up our system where we have our plus charge, and it would head in this direction, and we could say we could do energy conservation. We could say energy initial is equal to the energy right before it hits this. And so you could say E initial, energy, now not electric field, sorry, we've got bunches of E's running around. I'll try to keep my electric fields as having arrows above them, but this is initial energy, I'll call it mechanical energy initial, is the initial would be the initial kinetic energy, if it starts from rest here, the initial potential energy, which would be Q times V, the V initial, and mechanical energy final would be whatever final speed it had, final kinetic energy, and U final would be Q times V final. In this case, we would be at 0 volts, and then this would be 1/2 m little v squared, where v is the speed. And so I could just say Q times V1 is equal to 1/2 m the speed squared. And so from this, if I know 12 volts, I know how much charge, if it's the charge of an electron, which in this case would be a proton, I suppose, that would be released, and we knew the mass, then we could find out how fast it would be going once it got there. Okay? And so this is something that allows us, just like when we were doing this back in Physics 1, to find out information about a particle just by knowing the energies and knowing that it's going to trade potential energy for kinetic energy. Or if I'm halfway through, it's traded part of its potential energy for kinetic energy, but it still has some potential energy there. And so this gives us a way to start analyzing problems that just knowing the force is still, it's a little hard to get at this because the force is such that it's oftentimes not a constant force, because it's oftentimes not a constant electric field. So this expression that we have for the potential, the equivalent expression for the voltage for a point charge, okay, V for a point charge, this is not V for everything, but V for a point charge is just going to be the same thing we did over here, right? E was F over Q, so V is this divided by Q. So the potential, the voltage for a point charge is KQ over R. And so that's like saying if I have a charge plus Q here, this voltage, like if I come across this distance away, that R away, I can say that's however many volts, 7 volts. And that just tells me how much energy would be available if I put another little charge right there. Okay, so this is a way to describe what's going on, and a way to do it in terms of energy, but you probably have actually more experience with voltage than potential energy associated with electricity, because you're used to talking about 12-volt batteries or 9-volt batteries or 1.5-volt batteries. You're used to charging up batteries. That's what you're wanting to get to, a full charge, so that it has 12 volts of potential. Electrostatic potential is what we describe it as, which says when we put a charge in there, then we have energy.